All right, so yesterday we talked about in class about the binomial distribution. And the things you have to know for binomial is this: there must be two mutually exclusive outcomes. Win, lose, pregnant, not pregnant, etc., etc. That has to be true. Number two, you're going to play n times. So before you start, I'm going to shoot 10 baskets. I'm going to have 6 kids. I'm going to do this. I'm going to whatever it is. Okay, I'm going to roll the dice 7 times. Whatever it happens to be, that's what I'm going to do. And I'm going to do it before I ever, before I'm going to do it. I'm going to decide to do it before I ever do it. And then the last thing each play is independent. Okay, well, today we're going to change one of those. So the next 3 or 4 days, we're going to change one of those outcomes. And when we do that, we're going to come up with a different distribution every time we do that. Okay. Now, how, why, whatever. Okay, well, in this case, what we're going to be looking at is we're going to be saying, well, all right. So, for instance, suppose I have more than 2 outcomes. Oh, then it won't be binomial anymore. You see that? What if every time I play it's dependent? It's not independent anymore. Well, that's going to be different. What if I don't always play n times? What if I change the number of times I play? These are the things we're going to be doing. And every time we do one of those, it's going to change it. So today we're going to say, and I want you to picture this. Back in the day, you're out in the backyard shooting baskets or something. And mom says, get inside. And you said, no, mom, I'm going to keep shooting until I have to make one more basket before I come in. I have to make one more basket before I come in. Okay? Well, think about what's going to happen is, what's the probability that the first basket you make is the 4th shot? Okay, what about that? Okay, well, what would you have to know? Well, you'd have to know is make or miss. So it sounds binomial from that standpoint, yes? You make it or you miss it. Mr. Green, am I still a 70% foul shooter? By God, today you are a 70% foul shooter. Good for you, sir. Okay. Well, what do I know? If I can win on the 4th shot, what does that mean? Well, in my case, then I'm just going to quit on the first make. The first 3 shots then had to be misses. In other words, that's q to the 3rd power, right? And then times p, which is 0.7, times p to the 1st. This right here, this guy right here. Okay, in other words, it is q to the n minus 1 times p. This has a distribution. It's called play until 1 win. Okay? Well, Groom, what if he'd have finished on the 3rd try? Then he wouldn't have been going 4 times. Does that make sense? Well, what if he'd won on the 2nd time? Well, he wouldn't have gone 3 times. You know what I'm saying? It has to be it has to be that way. And so think about that as the time goes along. Oh my word. And kind of keep that in the back of your mind. This right here is what is referred to as the geometric distribution. And you will always recognize it because it is always play until I win 1 time. So on the old calculator here, 0.3 to the 3rd times 0.7 is about a 1.8% chance of that happening. Why is it so small? Well, duh, you're a 70% foul shooter, bruh. You're a 70% foul shooter. Oh, wait a minute. Groom, are you saying that there was a 70% chance that I make it on the 1st try? Yes. Furthermore, Groom, are you saying that there's a 21% chance that I make it not on the 1st shot, but the 2nd shot? I was trying hard not to say that, but yes, that's right. Wait. The probabilities are going down, Grim, aren't they? Yes, they certainly are. You miss 2, make 1. Oh. Miss 2, make 1 is point. Gosh darn it, you moron. Jay, you dummy. There you go. Give it to me, you hippie. There's about a 6% chance that you miss the first 2 and then make the 3rd one. Okay? And then for our case, we actually have a 0.0189 or a 1.89% chance that you miss, and then make, right? right? And why is that? Because you're a good foul shooter. You're a good foul shooter. You're a good foul shooter. So obviously is going to be a situation like that. Okay? Just got to keep that in the back of your head as you go along. You're like, oh, yeah, it's going to get worse and worse and worse. Now, that isn't true if you're a 20% foul shooter. So if you were a 20% foul shooter, it'd be 0.8 times 0.8 times 0.2. Then if you made it on the third shot, right? So 0.8 squared times 0.2. See, there's a pretty good chance that you'd make it on that shot because obviously 0.8 squared, right? Okay. So, like if you were a 20% foul shooter, there's a 20% chance you make it the first time. There's a 16% chance you make it the next time. Is that right? Right? Because you had to miss it and then make it, right? So let's do the math on that. You 0.2 the first time, and then it'd be 0.8 times 0.2. Dang it. Which is 16%. And then you get 0.8 squared because you had to miss it twice and then make it. And you get about 12.8%. And then keep going just for fun. And then 10.24%. Well, there you go. And so on and so on and so on, right? Okay, so as time goes on, you're like, oh. Now remember, this is the probability that your first shot is the first shot. The first shot that you make is the first shot. First shot you make is the second. First shot you make is the third. First shot you make is the fourth. Notice that binomial is saying, hey, if I shoot 4 times, what's the probability I make 1? Well, it's pretty good if you're a 20% foul shooter. It's pretty good. Okay, so kind of think about that as you go along. That's not what we're saying. But what we're saying is what's probably the first one I make is the 4th shot or is the 3rd shot, or whatever it happens to be. Okay, that's the idea here. That's how it's always going to be. Okay, when it comes to this guy, which is called the geometric distribution. Now, we can do several other ones here. I don't know. What are you? You are a darts thrower. Good for you. And you hit the bullseye. Bullseye. You're not very good though. 30% of the time. Woohoo! All right. And what's the what's the probability that your first bullseye is the 6th throw? I don't know. Let's find out. So, well, I'd have to have missed it 5 times and then make 1. Oops, miss it, I said. I had to miss it and then make 1. About 5% chance. Remember, it's not saying what's the probability that you get 1 out of 6. It's the probability that your first make is the 6th one. Anywho, so now let's change it up. Mom, I'm going to keep shooting. I'm going to shoot until I make 3. What's the probability that the 3rd make is the 8th shot? You can see it's similar to the last one, but this time I have to change it up. Now, if I'm going to quit on the 8th shot, that means I had to have shot 7 times so far. I've shot 7 times. And I've made 2. Question, does it have to be in any particular order? No. Well, now hold the phone a minute. You're saying that there's 2 outcomes, make or miss. Yes. They are independent. Did the order matter at all? That sounds binomial. Sure does. So it'd be 7 choose 2. And then it would be you're 70% foul shooter again, sorry. 0.7 to the 2, because you made 2 shots. And then the other 5 have been misses thus far, yes? These are your first 7 shots. What does the 8th shot have to be? The 8th shot has to be another make, yes? This has a name. This is referred to as the negative binomial distribution. The negative binomial distribution. I didn't make it up. I just work here. Okay? So if you're playing along at home, either bust your calculator out or get on Excel. Doesn't really matter to me. And we're going to get a combination. So we're going to go 7, 2. There you go. Times 0.7 to the third power, because there's 3 of them, yeah? Times 0.3 to the 5th power. Boom. There's a 1.7% chance of this happening. Okay? Okay? That's pretty straightforward, pretty easy to do. Okay? When we do these negative binomials, and now you're like, wait, Groom, what is the difference between negative binomial and geometric? Well, the geometric is just a special case. Special case negative binomial. That's all it is. You with me? Just like a square is a special rectangle. That's all it is, right? So it's similar, but it's just, different, as they say, right? So when we do these problems, kind of keep that in the back of your head. Now, on that last problem, we had 7 choose 2 times 0.7 to the 2 times 0.3 to the 5 times 0.7 again, right? Okay, well, what does this represent? Well, we asked about it happening on the 8th shot, so this is actually n minus 1. Choose. Well, I wanted to win 3 times, but 2 is 1 less than that, so x minus 1. And then times p, well, p to the x power. And then times q, darn it, I keep writing decimals, times q to the n minus x. So if you look at it, it looks binomial. It does look binomial, but we're 1 short on the combination piece right here. You with me? We're 1 short on the combination. Instead of n choose x, it's n minus 1 choose x minus 1. Okay? Nice. But you're like, Groom, what if but you said geometric is a special case. Correct. Geometric is special because, what is your x? Well, x is 1. Well, let's plug this in. Well, n minus 1 is still n minus 1. That's a fact. Choose. And then let's do this side over here. 1 minus 1 is 0. Oh, dear. What is anything choose 0? It's 1. Times p to the what power? Well, we need 1p. And then how many losses do you have? We have q to the n minus 1. And so this becomes just 1 times p to the 1 times q to the n minus 1. When I was a kid, they always made a big deal about writing it this way, which I like because the losses had to come first. Because by definition, it's the probability that your first win is on the nth draw or the nth play or whatever it is. Okay? Nice. Now, let's continue, shall we? Oh, poop. Now, for instance, let's say, Mr. Groom, is it true that if you were asking a girl out in high school, you're like, Mr. Groom, back when Mr. Groom was in high school, he's going to go ask a girl out until one of them says, yeah, I'll go to the dance with you. Would that be a good example of geometric? Well, it sounds like it from the standpoint of they can say yes or no. Okay. No, I have to wash my hair. I don't like you, Jay. Yeah, probably, or whatever. Okay, thanks for rubbing it in my face. I'm a horrible person. No one liked me, whatever. That's true, though. Is it possible, okay, that it's independent? I don't think the probabilities were independent, right? Like, well, maybe. If you were really a loser, yeah, nobody likes that guy. He has 0 chance with any of the ladies. Well, it's not much of a problem then, but okay, sure. So that's where it'd be a little weird, you know what I'm saying? If it was something like that. Now, normally, yeah, as soon as you get one person to say, yeah, I'll go to prom with you, you probably stop asking because you don't really need more than 1 date to prom. That just seems like a lot of money to be messing around with. You with me? So in that regard, I would say that, no, it doesn't sound very at all. It doesn't sound very geometric, right? Because the probabilities don't remain constant each time. In fact, it'd be really weird if they did remain constant, right? Like if you had a situation where you had enough people out there that you could go out and just randomly, here's a girl, I'm going to go ask her. Hey, well, it's about a 1 in 4 chance of going and saying yes. Well, that's weird. Okay, they'd all be different, right? And whether it's all 0 or whatever it is, it would just be weird. They wouldn't be the same every time. Okay, so you got to keep that in the back of your head. So it's gonna have to be things like throwing darts, kicking field goals, whatever it happens to be. Let's say rolling dice, Groom. I will quit rolling, or I will come inside, or whatever, when I get the 7th 5 on a dice. Dude, we're gonna be here all night, dog. What's the probability that the 7th 5 is on the 4th roll? And you're like, Groom, that can't happen. Correct. You'd have to roll it at least 5 times. Oh, on the 14th roll. Oh, there you go, dog. Piece of cake. So clearly, it's the first. I'm sorry, the 7th, not the first roll. The 7th 5 is the 14th roll. You with me? Anyway, yeah, that's awesome. Okay, and so here it is. So listen, if I'm on the 14th roll coming up, that means I've already shot 13 times. Yes, and I want 7 of them. So that means I've already got 6 of them. Yes. On a dice, there's how many? There's 1/6 chance of getting a 5. I've already gotten 6 of them. Right? And thus far, the other 5/6 of them, I've got 7 of them. That's a total of 13 thus far, yes? The next one I roll must be a 6th. And it's that easy. Okay, so on my calculator, 13, 6. There you go, times, parentheses, 1 divided by 6 to the, I'm just going to do the 7th power because there's obviously 7 of them, times 5/6 to the 7th power. Oh, good criminy. And it's about 0.17%. It's unlikely to happen, bud. It's unlikely to happen. Piece of cake. Yeah. Nice. That's the idea of these guys. Now, they're not very hard. They're not very hard at all. In fact, it's kind of easy. In fact, right? And so what we're going to be looking at is, well, the math's not terrible. Well, the math isn't terrible. Can I do it on Excel too? And the answer is, yeah, of course. Well, I'll say Excel or Google Sheets. Obviously, you will use Google Sheets. I feel like doing Excel, so I'm going to use Excel. And so in Excel, turns out you can just do this, equals negative binomial.dist. And so on the last one, so it wants to know how many failures did you have? Well, on this last one, I shot 14 times. I won 7. I lost 7, so 7. How many successes did you have? 7. Probability of success, 0.7, I guess, because I'm a 0.7. No, 1/6. I'm sorry, it's 1/6. And then 0, because I don't want a cumulative distribution. Boom. There it is, piece of cake. Nice. Now, can you do it with the geometric as well? Well, sure you can. So if you come back here, geometric is right here. Let's do this geometric one. That one right there, right? So you play 4 times that one. Remember that one? So if you're doing this one, it would be equals. Now you do a couple different ways on this one, but again, I like to teach the same way every time. It makes it easier for everybody involved. You failed 3 times. You won once. Probability of success was 0.7, comma 0. And there it is, 0.0189, 0.0189, or 1.89%. Right? Piece of cake. Now, easier, different, better, weirder, whatever ways. Yeah, there's other ways of doing them too, right? So it turns out there's another one here. Like if you remember this, equals geometric distribution. Actually, this one doesn't have it. That's right. That's right. Excel doesn't have it. Excel doesn't have it. The TI calculators do have it. If you have a TI calculator, it doesn't matter. I don't really care. The geometric is ridiculous. I just memorize it like this. Geometric, it's fail times 1 win. To me, that's the easiest. Okay. To me, that is just by far the easiest way of going about doing it. Yeah, because to me, it's just, oh, there it is, piece of cake. Nice. Now, again, not very difficult. Now, what about this? What is the problem? So listen again. Once we're going to do it again here. You are a 6-year. Nope. You're going to flip coins. Nice. Flip coins. Nice. Flip a coin until I get 2 heads. Nice. What's the probability that I get 2 heads by the 10th roll? Now notice that this is, it could happen in the first 2 rolls, it could have been the first, so in other words, you could do this, you could do make, you get head, that would work, yes. You go heads, tails, heads, or tails, heads, heads. Either of those would work, yes. There's some probability for each of those because that's an or situation. Or you could do, watch this now, tails, tails, heads, heads, right? Or what? Tails, heads, tails, heads. Notice I finish on the head. Why? Because I have to have the heads finish last, yes? Or heads, tails, tails, heads. Are you with me? Okay? So we have all these different outcomes there. And as we're looking at them, we're like, oh, okay, that makes sense in terms of, this is the different ways of doing it. This is what we call a CDF, just like yesterday when we talked about with the binomial distribution. In other words, it's the probability that this happens less than or equal to, less than or equal to 10. Okay? Now, what's going to happen each time? Well, each time it gets bigger, we've had one more failure, yeah? Because we still only had 2 headses, right? So in Excel, what we're going to be doing is, and I'm going to write this on a separate sheet over here. I'm just going to kind of brute force it for a second so you can kind of see it happening. Maybe I am. Piece of crap. Maybe I am. I don't know. Maybe I'm not. It's hard to say. Okay, so let's do this. Let's click here. Let's do this. So this is the number of failures. Failures. All right, and then this is, obviously, we're still going to have only 2 wins each time. There's your probability. So in this case, listen, you could have 0 failures. In other words, you could go 2 for 2, right? Right? And then whatever, we said by the 10th roll. By the 10th roll, you'd have had how many failures? I believe you'd had 8 failures by the 10th roll. Is that correct? Does that make sense? So when we do this, just kind of keep that in the back of your head in terms of that. And so this is equals negative binomial dot dist. And number of failures is 0. Number of successes is 2. Now, by the way, I'm going to put a $sign over here because I want that to stay put. Oops, no, I lied to you. Dadgummit. Oh, stop it. Stop it. No, I don't want that to stay put. Don't do that. Just A2, sorry. A2. There we go. Comma 2. Because I'm going to drag it down in a minute. Probability of success is 0.7, comma 0. Oops. What did I say? What was I the problem about? Oh, 2 heads, 0.5, not 0.7. I was like, what am I talking about? Mr. Graham, you don't listen to yourself. Nobody else does. It's fine. Sure. Oh, I don't want an equal sign there. She's upset about that. I don't know why. There it is. Because why? Because I got 0.5 times 0.5, right? So these are the probability of each one of them happening. Now, check this out. So this is the probability that x, probability that x is less than or equal to big X. Big X. Now, big X, what is big X? Big X, big X. This would be 2 rolls, 3 rolls, 4 rows, etc. All right, rolls, or flips of the coin or what have you. Boom. Okay, so here it is. So equals this guy. Boom. The next one is equals the sum of these two guys. Make sure this one gets locked in with the dollar signs. And then drag it down. Boom. So the probability you get 2 by the time you get to this guy is 98%, because it's this plus this, this plus this plus this, this plus this plus this, and so on and so on and so forth. It keeps adding up as we go along. Okay. I'm going to pause one moment, please. Well, I guess that's better than nothing. Anyways, yeah, so there's that. And yeah, so negative binomial and the geometric distribution. They're pretty easy to do. Not hard at all. Again, play until you win once, then I'm stopping. That is the geometric distribution. Obviously, if you're only going to win once, you had to lose, then win, right? If you're going to play until you win n times, well, then you had to win n minus 1 times, right? First, right? And the first however many plays you've done, you had to win x minus 1 times in the first n minus 1 plays. And then the last play, the nth play, has to be your last win. Okay? So pretty easy to do. Now, as we go in the next couple of days, we're going to introduce a couple more. We're going to change a couple of our other ideas. Okay? So it's kind of neat. You'll see how they build out from there. All right, that's enough yabbering for today.